Okay, let me give you an introduction. So what I will talk about in general is a setup which is basically visible here, which is an optical cavity. For me as a theorist, that is just consisting of two mirrors facing each other. They trap light in such a confined geometry. Now I don't see my mouse anymore here. And now if you put an atom inside of that cavity, what you actually get is enhanced light-matter interaction. But what I want to look at is many atoms in the cavity. So just like in the previous talks. And then also you add an external pumping, which is basically visible here by the central peak. Yeah? And then what happens is those atoms will scatter light into the cavity, and that photons inside of the cavity can now bounce back and forth between atoms, effectively engineering interactions between the atoms. So what happens is, because of that light, the atoms start to interact. So this is not working very well, but I hope I can manage. So now what we have is, because of that light we inserted here, we have an interacting atom-atom system, because they talk they talk via the light. Now what we can do in addition is we can add up frequency tones that excite the new now interacting matter. And this is basically the idea of all of this. So we basically want to add these frequency tones such that, okay, not very well, such that we can resonantly excite certain coherent spatiotemporal patterns. But okay, that's dangerous, right? So when I do this, suddenly, especially resonant excitation typically creates a lot of excitations. And then this system can heat up and whatever. And that's what is so fascinating in this system. You have also dissipation. And that means photons can leak out and energy can actually be removed of the system. And this can then eventually, or possibly, stabilize certain patterns in a long time behavior. Yeah? And basically the workhorse, what I think is a very nice experiment that realized this, is this experiment in Hamburg, done in the group of Andreas Hemmerich, done by Hans Kessler, where they generate such a system which is periodically modulated, and this is called a dissipative time crystals. I usually know that there is people contradicting with talking about time crystals here. I just use that terminology. I hope that's okay for you. So, okay. But what you see probably is I'm looking at the atoms. I'm talking about interacting atoms, exciting spatiotemporal pattern of the atoms. I'm not so much.
Which aspect of time crystal are you emphasizing?
So you have a coherent, you have macroscopic coherent in the cloud. This is one thing. I will mention this later on. And then also you break a time translational symmetry. So in fact, the drive gives you a certain period, and this will not be in
down conversion or something like that.
Yes, in fact, it's something like this. It's a parametric excitation. I will come to this. Yeah? So, and then the question is, in such systems, can we actually eliminate the cavity degrees of freedom, such that we can get an atom-only description that describes then, first of all, why is this important? Because this gives me a more efficient description of the dynamics, right? If you want to study two charges interacting with each other, you don't want to simulate the field, right? So you want to integrate that out. And the same logic I want to follow here. So it's a more efficient description and possibly can also give me some analytical results. And what is the challenge? Well, first of all, we need to describe the interactions correctly, the resonant excitations of these interactions, and also the dissipation, because we know that is important for the long-time behavior. Okay, the system that I want to study is basically this. It's the periodically driven dissipative Dicke model. My starting point is basically described by such a setup over here. You have a master equation. This density matrix rho now still consists of the atomic and the cavity degrees of freedom. The first part is the coherent dynamics of this density operator, governed by some Hamiltonian H. And the second part is just photon loss. So kappa is just the line width of the cavity, just means leakage of cavity photons. The Hamiltonian has several parts. The first one is a spin component, so it's a Z component with an energy omega naught. So this is the energy of the atom without interaction. Then there is a photon term, which is here described by this frequency omega c. And then some interactions of the cavity field with the spin X component. Important is here, in this description, very similar to what Jonathan said in his talk, this is not an effective dipole. So here you have here you have counter-rotating terms. Like the sigma x typically consists of sigma plus and sigma minus. So you can also create a photon and flip the spin in the other way. And that is achieved via some dynamical process and typically Raman transitions, because you have these scattering processes here that can flip the internal state and also result in a cavity emission. So this is an effective this is already an effective model where that describes some underlying system. Yeah. And those frequency tones that are visible here in this sketch with the center peak over there and those sidebands over there is basically just described by the coupling, which is modulated in time. So the central peak is just this G0. This will then, in the end, trace the light field with the atoms. And those sidebands is basically this cosine omega t. These are the two frequency tones that are shined in that modulate then the interaction between light and matter. Okay. I want to actually highlight here that I am not working in a very strong light-matter interaction regime. So the light and the matter are only traced very weakly. That means, in fact, this G0 is quite small. Yeah? And in fact, this results then in an effective weak tracing of light and matter. And what I want to do instead is I want to argue these frequency tones that are described by this G1 here and the frequency over here, they excite the interacting matter system. This is basically visible by this phase diagram over here. On the y-axis, you see G1. On the x-axis, you see the driving frequency omega. And then this is the order parameter. So this tells you if there is macroscopic coherence in the atomic medium. And then you see these so-called Arnold tongues, one over here, and one over here. And they typically happen at certain resonances. Here, this is given by a resonance frequency that I'll explain you in a second. Here at 1, at 2, and at something like 1/3. And this resonance frequency is basically just given by the bare atomic frequency, so just if you have a non-interacting system. And then, because of the weak tracing of G0, it is slightly modified because now these are not, you cannot completely separate light and matter anymore. So those are actually the trace state resonances. And parametric resonances means this is the underlying effect that was already mentioned here. So what you try to do is you try always to create pairs of the underlying matters. This happens whenever an integer value of the driving frequency is twice the resonance frequency. So that means each quantum of the driving frequency creates pairs. Yeah? And these time crystalline phase are now, I think, quite easy to understand. First of all, they are super radiant, so you have a lot of excitations in the system. So you have this x squared, large x squared. And second, you have a subharmonic response. And you might now expect that you can have a subharmonic response because you always excite pairs. That means the underlying matter will basically resonate with the omega res. But omega res, for the first resonance, n is equal 1, is just omega over 2. So it's a subharmonic. And then in the second term over here, n is actually equal to 2, and then it's not subharmonic. So this one, according to this definition, would be a time crystal. This would be not a time crystal just because it's a higher parametric resonance. This would be a time crystal again, and so on. So it's just basically understood in these simple terms of parametric resonances. And this is, in fact, I would say the most simple toy model for these dissipative Dicke time crystals. Okay, we want to eliminate the cavity and, yeah?
So one question.
Yeah.
This is different from the model by, can you go back one second?
Yes.
is different from the model of JÄGER, right?
Yes, it's slightly different. So this, the scheme that I show here is actually the one which is given by Schitra and Silberberg when they study the periodic driving, while what this paper of Ueda does, which is the second one here, and which actually connected this to time crystal, is always quenching across the transition, going below, quenching across the transition. But in the
touch the transition.
Yeah, I don't touch the transition. I don't touch the transition. That's, I think, the excited thing also here. Yeah? So I never go across the transition.
So you would, in principle, you would be able to do that in a light matter system without superradiant transition. You would not need to have photon condensation above a critical value of decoupling. I could change model.
So what happens here is like you still have macroscopic excitation of photons, in fact, which is actually comes from the matter, exciting the matter, and that will start to constructively emit into the cavity. But this is not something which happens because I cross the superradiant phase transition. It's something which happens dynamically. Yeah? So I resonantly excite pairs in the bosonic matter.
Many of times you don't need a Dicke model. You could do that with James Cummings?
No, because I need the counter-rotating terms.
You need a counter-rotating.
I need the counter-rotating terms because the counter-rotating terms are responsible for the J plus term. And the J plus term is exactly the term that I need. Yeah? What?
I was thinking if you consider a James Cumming like, but in an exotic, like regime where you break, you drive it, it's called something else there.
You need something which does not commute with it. Yeah.
The counter-rotating terms, so ultra-strong coupling, things like that, which you don't have. Sorry.
Oh, yeah. That's okay. That's okay. Okay. So. And I want to eliminate the cavity, and this is based on some other work that we had, which quite generally describes predicts Lindblad master equations for such cavity systems, also in the multimode case. But I now focus only on the single mode case. So this basically consists of two steps. The first step is because I want to move into a frame. I kind of want to move into a frame where the light and the matter is even weaker coupled. And this is done by a Schrieffer-Wolff or Polaran transformation, which basically slightly, weakly dresses the light field with the matter. This is basically described by this D over here, and this exponential, where you see here the cavity mode. And here's some spin, or some, in general, atomic operator alpha. This is the very general operator alpha. Now what you want to do is, you want to say now, okay, in this new frame, after you have done this displacement, you try to get the atom and cavity decoupled. And you try to get them decoupled up to a certain order. And what you can basically show that in up to third order, let's say, then this alpha needs to fulfill a following equation of motion, which is just given by this. And this has several terms. So I typically call this the effective field operator because it reminds a lot of the cavity field that you would typically study. Because here, it has just the response of the bare cavity. It's just the omega c and the kappa. So this is just the decay and the frequency of the cavity field. And then also it is driven by the underlying matter. So you get just a typical inhomogeneous term in your differential equation, which is just this. So this is a drive. And this drive is now an operator, okay? All of these are operators, and it's also time dependent. In addition, what is really crucial for us is this last commutator over there. Because that last commutator, which basically describes the field and with respect to the atom, is a retardation effect that tells you when this operator alpha converges to a steady state, it has some memory of the atomic evolution. And this atomic evolution is here just described by the bare precession, so just the omega naught times z. Yeah? Okay, and once you have done this, so what you basically now try to do, you can solve this typically in steady state. Yeah, you can try to integrate this to infinity. You apply this transformation and you simply project onto the vacuum state. And what you get then is a description just for the atomic degrees of freedom, which are now governed by a new master equation, which first has a coherent part with an effective Hamiltonian, and then also a decay part, which is the second term over here. And I want to show now here, because of the cavity, because of this effective field operator over there, we have beside the normal motion of the spin, also the coherent cavity-mediated interactions described by this red term, and also the cavity-mediated dissipation, which is basically done by this jump operator alpha. Okay. Okay, now of course there are some limitations, and the typical limitations why this is justified is a timescale separation. Okay, so what I really rely on is that the cavity degrees of freedom evolve much faster than the atomic degrees of freedom, such that the cavity can always decay quickly to an instantaneous state. And that's typically true if kappa and omega c are by far the largest frequencies. Yeah? So and then in that case, then I can eliminate the cavity degrees of freedom. I want to state, however, that this is not it's not getting completely rid of all retardation effects. Okay, so it's not just an instantaneous adiabatic solution, and it's actually important. So when you actually calculate these field terms, which are now decomposed in raising and lowering operator of the spin, you get the typical adiabatic component, which is just saying you throw away any retardation effects. The cavity is evolved so fast that it doesn't see that the spin does any dynamics. Yeah? But it also takes into account higher order effects. The one, which is just the retardation effects with respect to the drive. While the cavity relaxes, it sees that the drive has changed in time. And the other one, this last term, is because while the cavity relaxes, it sees that the atom has done some free evolution. And these are like these are basically, strictly speaking, higher order terms. Yeah? Okay, and this is then typically called in some languages this is the pure adiabatic term, and these are retardation effects. Okay, now I want to show you why do we use such a toy model, because we can actually compare it to the full model and check whether it's good enough. And this is what I show you now, and I want to show you this especially in this time crystalline phase over here. So the full quantum dynamics can still be studied with the atom-only description, but also with the atom cavity description, but only for small atom numbers. Yeah? So like 10, 20 atoms, and this is just a comparison here. So what I have to do, it's a time periodic system. That means my Lindblad is time periodic. So I have to study the Floquet Lindblad. Yeah? So I have to do Floquet theory for the whole Lindblad system. And these basically are described by this Floquet Lindblad over here, and then some eigenvalues lambda. And this is what you can see here. And it's the Lindblad dynamics. That means the Lindblad has typically real and imaginary part. The real part describes damping, and the imaginary part describes the oscillation. And what you can basically see here for atom numbers up to 20, I compare those to the two methods. The circles are the full atom and cavity dynamics, and the crosses are the atom-only description, and they agree extremely well. So this is the first hint. Then what we can, of course, also do now for n is very large, I do not have access to the full quantum atom cavity dynamics, but I can still rely on semi-classical methods, as we have also heard them before. It's a truncated Wigner method. And here, this is basically visible as this is the dynamical plot, so this is time, and this is the superradiant order parameter over here. And the atom plus cavity semi-classical dynamics is visible as dashed line, while the atom-only quantum dynamics is visible as black line. And you see them, they both overlap extremely well. Yeah? And this is in a superradiant phase. Yeah? So this is actually a macroscopic coherence here. So this is really superradiant, and still we find very good agreement of atom-only description. I want to mention this has, of course, two things. First of all, it shows that we probably do not need to, so the retardation effects we have taken into account are enough to describe this relaxation dynamics. Is the first thing. This is the good thing. The bad thing is, of course, a little bit, well, that's a semi-classical description. So the dynamics is most likely more or less semi-classical. Yeah? So, but it's a good check still. Yeah? Okay, but we can also study something purely quantum. Yeah? So because now we can actually access atom number with the atom-only description, which are of the order of hundreds, 100, 200, 300 atoms. Something which you cannot do with a cavity, because you pay a price twice. First of all, you have the cavity degrees of freedom, and you have a cutoff in this cavity degrees of freedom, and this cutoff needs to increase with the atom number, because the cavity field increases with the atom number. So this is a huge speed up in a way for this model. And the time crystal breaks actually a discrete time translational symmetry. That means we should expect in the Lindblad spectrum a closing gap exactly at half the driving frequency. And a closing gap means that the decay rate gamma actually vanishes in the thermodynamic limit n to infinity. That's what you should have when you have a symmetry breaking, right? And this is what I show you here. So In A, this is actually in the time crystalline, this is outside of the time crystalline phase. This is visible here. So this is gamma over kappa as function of n. And B, this is this figure over here. Again, gamma over kappa divided by gamma over kappa as function of n. And outside of that time crystalline phase, what you actually see here, it converges to some value which is different from 0. So that means the system is still gapped. It's outside of the time crystalline phase. And for inside of this area, you actually see it exponentially increases. And you can see that because here I plotted this in a log scale. Yeah, and this is, and you can see that this actually, in order to study this, you need to go to hundreds of atoms. This is something you cannot see with the cavity. Yeah? So this is why we highlight here that this is kind of the first description of this effect, actually, with this Lindblad description. Okay, there's also something else. Of course, one can now try to also study some physics doing an additional approximation. This additional approximation is a mean field description. And I do a mean field description in a slightly different way than you have probably seen this before. So what I do is basically instead of studying spins, I transform those spins, x, y, and z, so the collective spins, into Schwinger bosons. And then I do a mean field approximation on basis of the bosons. That means what I want to describe is a classical equation for this phi s, which is now just a C number. And from this description, you can basically show that there are two coupled differential equations for phi down and phi up. They are both coupled, and they are also nonlinear. So all these interaction effects and also dissipation effects result in a nonlinear equation for these phi up and phi down. And just to highlight this, if these V0 and V1, they basically come from the cavity. So if you just remove them, you see you have just omega naught, which is just a linear term. Yeah? So really this cavity gave rise to these nonlinearities. And you also see that the V0 always has an imaginary part in front of it, while the V1 is always a real number. And that has as a result that these V0 are actually coherent terms. So this V0 completely results from the time-dependent interactions. It's a time-dependent object which is on interactions. And the V1 is a dissipation effect. And what one can show is that this V1 is the imbalance of the cooling and heating sideband. So from this very simple description, one can get a physical intuition of what dissipation actually does. Yeah, almost done actually. So just to explain you a little bit what I mean by this. So in fact, what we have is a cavity. So this is just the Lorentzian of the cavity. And if you would have just scattering of laser photons in there, yeah, there's a characteristic frequency of the laser photon, which is over there. But now this laser photon hits the atoms, and the atoms makes a transition to spin up, from spin down to spin up, or vice versa. And because of that, there's an energy, right? And this energy has to be compensated by the laser photon. Yeah? So the scattered laser photon is on somewhere else. And when you go from the up state to the down state, you get some energy. So this laser photon is blue shifted, which you can basically see here. When you go from down to up, so then you actually need some energy from the photon, so the photon is redshifted, which is over there. And now these two photons are in the cavity, and because this photon has a higher outcoupling rate, it's more likely that the system removes energy from the atoms. So that's an effective cooling procedure. It's just a probability feature that tells you energy that photons that carry more energy are more likely removed from the system. And now we can make that test. We can actually study, with theory it's easy, we just can remove dissipation by setting V1 is equal 0. So when I put V1 is equal 0, what I get is this red curve. So this is the full spin trajectory of x, y, and z. And you basically see it's a wide oscillation. There's no energy ever removed from this. While when you look at the black curve, which is V1 is different from 0, you see a very nice limit cycle. Yeah? So this really stabilizes this on a stable orbit. Okay, with this I'm at the end of my talk. So I hope I could give you this introduction to this effective master equations, which describe in a way a more efficient description of interactions and dissipation, and then also describe with this the time periodic dissipative Dicke model. the exponential closing gap, and some new insights in this form of cooling mechanism and the stabilization mechanism. I also want to show, because that is a parametric process, the direct intuition is that should also be useful for metrology. So we also have some work where we actually use this on a short time scale to generate squeezing. And with this, thank you for your attention.